Okay. Welcome everyone to the Turbomachinery session. I'm Professor Håkan Nilsson from Chalmers University of Technology. I'm sharing this session. We have three presentations in the session with 20 minutes each, and I will give a sign to the presenters after 15 minutes, and then you should start finalizing so that we have some time for questions as well. We start with questions from the audience, and then if there's time left, we can also take questions from online, but those who are online should then ask the questions in the Q&A for this particular session in the WOVA app. So we keep track of those questions, and the presenters can answer them later as well. Okay. We'll start with the first presenter here, which is Jonathan Fahlbeck, who will be presenting cavitation simulations of a low-head contra-rotating pump turbine.
Yes, let's see if we can maximize this or presentation mode. Yes, good. Everyone sees. So my name is Jonathan Fahlbeck. I will talk about cavitation simulations of a low-head contra-rotating pump turbine. This work is made together with Håkan, who is the chair, Syed, and Mohammed at Chalmers University of Technology. So first off, what is a contra-rotating pump turbine? And I will also cover the Alpheus project. So the contra-rotating pump turbine is an axial flow pump turbine, and in this upper figure, let's see if we can have some laser pointer perhaps, so the online audience can also see. Oh, there is no laser pointer. Oh, there. Yeah, yes. So you have two runners rotating in opposite direction from one another, and this figure here shows a conceptual mounting arrangement that later on will be used in experimental test case. This is an axial flow machine. It's intended for low head and high flow rate, where low head is sort of the height elevation between the two reservoirs in a pump storage facility. And pumped hydro storage, as you hear by the name, is energy storage by hydropower. And it provides grid stability, but also as a key corner in order to have a fully renewable energy systems in order to cope with variation from energy production from, for instance, wind and solar. So typical layout is we have upper and lower reservoir, and in times when there is a high energy surplus, we can pump water from the lower reservoir, and then we can release water from the upper reservoir when there is a higher demand from the electrical grid. A problem with pumped hydro storage is that it's traditionally developed for high head situation, meaning that there is a large height difference between these two reservoirs. And for that reason, the Alpheus project was formed. It's a European research project where we evaluate three different runner configurations intended for low head pumped hydro storage. So we can enable pumped hydro storage in countries that lack high mountain regions, for instance. And in this Alpheus research project, we will be running experimental tests of this contra-rotating pump turbine. And this figure here shows a graphical representation of the future experimental test facility. So we have an elevated tank and the lower tank, and the model scale diameter of the runners are roughly 30 centimeters, whereas in a prototype scale, we would look at diameters of roughly 6 meters. So this is quite small scale compared to the prototype scale. In the simulations, we place the numerical domain close to the runners, as we can, for obviously reasons, not afford to resolve the entire hydraulic system. And in these experimental test facility, we've seen that there may be a problem with cavitation. And when assessing cavitation, a usual number is something called the sigma number, which is a measurement how large is the risk of cavitation, you can say. And this formula just shows the calculation of the sigma number. So H lower is the height elevation of the lower tank, and then HCRPT is the head produced or extracted by the pump turbine. But as you can see, this is a larger hydraulic system. So in order to achieve reliable flow conditions, we also need to take into account the various components that are not part of the numerical domain. So for instance, flow meters and valves, etc. And in order to do that, we developed a boundary condition called head loss pressure boundary condition, where we essentially uses the Bernoulli's equation between the parts that are not part of the numerical domain, but is in the experimental test facility to describe local and friction losses for the hydraulic system that is not part of the numerical domain. So for instance, this entire blue part will be modeled at the boundaries of the numerical domain. And we set the static pressure according to this equation. But since position 1 here is large reservoir, we can neglect that there is any flow velocity at the reservoir. The boundary condition furthermore allows for any number of local or friction losses, but it can also have some time varying properties. And important is the inflow losses are subtracted and outflow losses are added. And it's currently developed for an incompressible flow case. And the source code and also paper is available at the OpenFOAM journal, so you can please have a look at it if you like. And more interesting, how the cavitation simulations are carried out. I use the OpenFOAM version 2112 together with the interface change DM foam solver. And in this solver, I use the Genoa cavitation model, which basically is a mixture fraction model. So you solve one set of the Navier-Stokes equation, you don't solve two separate Navier-Stokes equations. With this Genoa model, so you basically track the volume fraction, which is denoted alpha here. And I just want to comment that if you use this solver, please use the mule corrector. And I'm saying this because one of our neighboring departments at the university have developed their own shower model, and in their solver they don't need to use this mule correction. So initially I did not use this mule correction, and that made the simulation blow up. So if you intend to run cavitation simulation, use the mule correction. And then I also prescribe the head loss pressure boundary condition at the inlet and outlets, turbulences model with the K-omega SST SAS model. And in this figure here, you can just see a view of the mesh, which is divided into 4 different cell zones, and the cell size is roughly 12 million cells. And for the convection terms of the 3 momentum equations, the last scheme is applied, and for temporal discretization, the backward scheme is applied. And in this study, 4 different operating conditions are evaluated: 2 in turbine mode, where we change the height elevation of the lower reservoir, and then 2 in pump mode, where the rotational speed is changed of the runners. So just a quick view of how the computational domain is characterized. So 4 different cell zones, 1 low pressure zone, 1 high pressure zone, and then we have the 2 runners. And the AMI interface is applied to transfer fluxes between these 4 regions. And the 2 runners rotate individually by describing a solid body rotation to the runner domains. And here's just a clarification of where the head of the machine is calculated. So it's based on the total pressure over this small area here. All right, so I'll start with case A, which is in turbine mode. And in case A, I use the lowest height elevation available in the lab in the lower tank. And you can see the run rotational speeds here. And if we calculate some nice numbers, we can see that we have a sigma value of roughly 1.44 and then some power of 17 kilowatts. And they have some flow rate and net head of the machine as well. So looking at the isosurface of the volume fraction, we can see that we have some small amount of cavitation at the leading edge of the downstream runner in turbine mode, but in general it's almost no cavitation present. But starting with or continuing with case B in turbine mode, so now we actually increase the height elevation of the lower tank. And that is the only difference between case A and case B. And then if we compute these values again, we can see that because of that, we increase the height elevation, we will have a larger sigma number, but we will also have a lower flow rate and net head of the machine. And if we look at the isosurface, we actually see that the machine can operate completely cavitating free, which is very good for the experiments, because in the experiments, we initially don't want to have any cavitation disturbing the measurements. Moving on to the more severe cases, which is pump mode. So we start with the design point, and I should point out that in pump mode, we will always use the highest height elevation in the lower tank, but instead we will change the rotational speed of the runners. So looking at these computed values again, I will start pointing out with the sigma value, which is below 1 in this case. And then we also see that we have a much higher power, flow rate, and net head in pump mode compared to in turbine mode, but we also see a quite large decrease in efficiency, which I will talk more about in the coming slides as well. But if we look at the isosurface of cavitation again, or volume fraction, we can see that in this case we actually have quite severe cavitation around the upstream runner in pump mode. We can, for instance, see that almost this entire blade is fully covered by a cavitating cloud. And if we compare the computed power, flow rate, and efficiency with running simulations where we don't include cavitation, so also this is just a single phase simulations using the OpenFOAM solver, we actually see that there is quite large difference between the efficiency, for instance. So there is quite large efficiency drop caused by this cavitation in the pump mode design point. So we wanted to find an alternative operating conditions where we lower the rotational speed of the runners in order to see if we can have a better condition in pump mode that can be tested in the test facility. So here we will have a larger sigma number, but also a reduced power and flow rate. Luckily, we also have an increase of efficiency. And if we look at the isosurface of the volume fraction again, we can see that for sure we still have some small amount of cavitation at the leading edges of both runners, but overall the amount of cavitation is quite drastically reduced by reducing the rotational speed of the runners. I should point out that I tried to reduce rotational speed of runners even further, but then we start to see problems with much worse efficiency and so on. So this is a sort of good trade-off between good efficiency and small amount of cavitation. Here's just a comparison that we see that there is very small difference between running simulations with and without cavitation. But also to explain why there is a large difference between the cavitating flow simulation and the non-cavitating flow simulations, I will show the static pressure along this line here. So this actually goes from the leading edge to the trailing edge, and it goes both on the suction side, which you see here, but also on the pressure side of the blade. So we first look at the non-cavitating flow simulation. So we have case C, the design point, and case D, where we have a lower RPM, and from the leading edge to the trailing edge. And here we actually see the absolute pressure. And what we can see, especially at the design point, is that we have non-physical negative absolute pressure, which is totally fine if you run the simulations that don't care about cavitation, right? But if you're going to test this experimentally, then of course this cannot be the case. We also see that in the case D, there is some small part where we have non-physical pressure, but most of the static pressure is above the vapor pressure or zero pressure. So just to make comparison, when we have cavitation, we can see that the pressure distribution around runner blades are totally different for the case where, for the design point where we had a lot of cavitation. Whereas if we look at the case D, where we had much less cavitation, we can see that for sure at this point, close to the leading edge on the suction side, there is some small difference, but in general, the pressure profile is very similar to the case where we don't consider cavitation. And then going into the final slide of presentation, what we can see is that when using this sigma number, we can see that there is actually some mismatch. So if we look at case A, we can see that case A actually have a lower sigma number compared to case D. But if you remember so this is case A in turbine mode, and this is case D in pump mode. You can see that in case A, we have a lower sigma number, whereas in case D, we have a higher sigma number, even though we clearly have more cavitation in the case D. So one of the partners in the Alpheus project designed a new cavitation parameter that hopefully could capture the risk of cavitation to a greater extent. I will not go into detail, but here you can see the general calculation of it. And what we can see is that if we compare case A and case D, is that case D show a lower, this cavitation parameter show a lower risk of cavitation compared as to case D, which should be the case. So this new cavitation parameter is perhaps a more suitable way to look at cavitation compared to this sigma number if you don't have a very good knowledge of how your machine work at all possible operating conditions. So just some conclusions. We can see that we carried out some cavitation analysis for the contra-rotating pump turbine, and we prescribed the head loss pressure boundary condition at the inlet and outlet of the numerical domain. In turbine mode, we could see that we had some small amount of cavitation in case A, and in case B, we could actually see that we could operate the machine in cavitating-free conditions, which is good for the experiments. In pump mode, though, we can see that at design point, we had quite some severe cavitation, whereas if we reduce the rotational speed, we could also reduce the amount of cavitation quite substantially. So hopefully that operating point can be tested in the lab facility in the future. Another thing that I want to do in the future is to perform a full, something called a full head breakdown curve, where you basically just change the static pressure on the low pressure side until you see a large drop in efficiency. But that will require that I need to run the simulation in a totally different way than I set it up now. And this point here, for those of you who listened to my talk last year, then I said I would like to validate my numerical framework. That is still up here. So hopefully next year when I come here, I can show some validation, but I'm not promising that. So thank you very much for listening.
16 minutes now, so
Yeah, okay.
so we'll have some time for questions.
Very interesting.
Hmm?
So, okay, I want to start with the
No, it's a solid body rotation of the, I can see. Yeah, now I have a lot of fancy. So I prescribe a solid body rotation on this red zone here, and then I prescribe another solid body rotation on the blue zone. So the entire mesh region is rotating. So it's not some overset mesh, it's the entire mesh region is rotating. Yeah, the question was if how the rotation of the runners were prescribed, and the answer was that it's a solid body rotation. And sorry, your next question was. I just used the the question was if the source code is available online, and yes, because the solver, I have not modified the solver in any way. This is part of the standard OpenFOAM library. So you both have it in the pimple foam solver, but also in this interface change the foam. This solver interface change the foam. It is the interface change foam solver, but with the possibility to have a dynamic mesh motion. So it is already part of the solver. So I've not changed the solver in any way. So this is part of the ESI version of OpenFOAM. I guess it's also possible to use in other versions of OpenFOAM as well. Yeah, the boundary condition, of course, that is available online with the source code and also the paper.
But
So we have another.
It is the muse corrector in the tutorials. Is that activated?
Yes, the muse corrector is activated in the tutorials. The only reason why I did not activate it was because of our neighboring department who have worked a lot on cavitation. They don't use it, so I thought, well, why should I use it? And that was stupid. Yeah. Yes, so the question was if there is any advantages of using the K omega SST SAS compared to the K omega SST? And the simple answer is yes, because with the SAS modifications, you allow for a decrease in the turbulent viscosity, so you actually resolve part of the turbulence in the numerical domain. But this is, of course, done automatically via a function, so most likely you would like to verify that the SAS model is appropriate for your case. But in general, I would say that you will get a more accurate solution using the SAS simulations. I also tried run simulations using only the SST model, and I don't like what I see, if we put it that way.
Yeah, good morning. My name is Kang Seung-hwan from Korea Aerospace Research Institute. And I want to talk about the improvement of compressible MRF solver for gas turbine analysis. So the content is first of all, in the introduction, I will explain about the background and some information about this. And I want to talk about some issues in this project. The first one is the mixing plane program, and the second one is wall temperature risings. And then I will sum up and conclude. So in the CFD field, and including the gas turbine, high fidelity analysis is required, and which means the more grid is necessary and more calculation capacity is also unnecessary. And like this example, if you use the large eddy simulation, you need to use lots of grid and many computer source. So and then massive parallel computation is favorable, but using the commercial code is very burden. Fund burden. So we thought the open source CF code is necessary because it is without license code. So it is gonna be the alternative method. So and then we chose the OpenFOAM. It is very well known for the open source CF code. And for the analysis of turbomachinery is for example the compressor turbine. It is usually consists of the stator and rotor, and they have the periodicity, which means you can use the periodic interface, and they have the stator and rotor, which means they have the interface between them, and they have some stages, so also they have the interfaces. And so the interface utility is very important to analyze this problem, but in the normal version of OpenFOAM doesn't provide this function. Only we found that only these functions are provided by OpenFOAM Extended, which is the community-driven version. So what you found is that previously some researchers are already done their work with for example the interface like a mixing plane here, and some researchers already done about the compressible MRF solver. MRF means the multiple reference frame or multiple rotating frame. So so we wanted to just use them, but using these things, we found out some problems also. So I want to share what the problem was, and how can we solve the problem. And here the compressible solver, the author I emphasize that here they use the rotor phase jump, and I will talk about later. And and one thing that I want to share with you more is that the thermal physical property. We are using the compressible fluid, right? So which means the fluid properties are varies depending on the temperature, usually temperature. So we have to choose some options like here, the Sutherland, pure mixture, perfect gas, and then we can use like this thermal conductivity and dynamic viscosity depending on the temperature. And also, the more importantly, we need the CP, the specific heat capacity at constant pressure of air according to the air temperature. But the only option we can use is the GenF option, it's called, and you can find how to use the GenF option by reading the user guide. And here, and we there is some example of the coefficient, but we have our cup, so we used we made our one coefficient, and we adapted, we used it. And so and we want so I wanted to share with this information with you because there was not much information about this. And the normal version of OpenFOAM, I have to say the platform is like this one, and you can see more but I can see it is more directly, and it is more good to see. But in the foam extend version, it is very hard to see. So you need to the care must be taken well. And this is the default condition. And in this project, first of all, we didn't use viscous heating term here. I will explain it later. And we are supported by the supercomputer from KIST, Korea Institute of Science and Technology Information. But the problem is that the OpenFOAM 4.1 version didn't provide the how to say the multiple parallel nodes computation, which is very sad. I mean, we just used the one node with 68 cores, which is the maximum cores, and then okay, and we used the various turbine geometries. Like one of them is from CFD tutorial, and one of them is our design, the Parry design, the cold turbine, and the another thing is the NASA GE E3 energy efficient engine low pressure turbine. And using the OpenFOAM and the simulating this problem, we met some problems. So many problems actually, but some of them I want to talk about. That is the maximum mixing plane and wall temperature problem. So before start the mixing plane issue, we need to review about the Rothafi. This is the how you can derive the Rothafi definition. The important thing is that Rothafi is preserved conserve its value from from the inlet to the outlet, and it is like the total enthalpy. I mean, if there is no rotation, Rothafi value is like total enthalpy, and the definition is like this equation. So it is total enthalpy plus more term. So it is called U rotation. U rotation means the blade rotational speed, and the C theta or U theta means the working fluid tangential velocity, and this multiplication is called Rothafi jump. And there is another definition of the Rothafi by using the velocity triangle. So you should remember this. And if you use the mixing plane, and at first after the first installation of foam extend, you can meet the warning message here, but with this warning message, you can solve the problem, but the answer is the answer is wrong, because it says that some variable was not found. It is because of they missed the uppercase and the lowercase letters. So the answer was the result gets wrong answer. But thankfully and fortunately, there is in the Safety Online and in forum, some user already made the solution. So I just followed this instruction and I made this code correctly, and I could make the mixing plane problem correctly. So here the rotating jump worked correctly, and the enthalpy or temperature is calculated continuously. And you can see that the foam X10 is a recently released new version 5.0, and here another compressible MRF solver called the CD compressible MRF foam. Here this issue was solved. I mean, the problem was corrected, but unfortunately, in CD universal MRF foam did not change it. Did not change. So you should care also. And another problem is that when I solved the multi-stage, I got some error in the interface of between stages. Here you can see that it is the reference from the CFX solution, but the foam X10, you can see the discontinuity in the temperature field. This is why the reason is this, that here the rotary definition and the U theta and U rotation are on the same vector plane, but they can be opposite direction. The example is like this one. The rotation is going right side, but the real absolute velocity goes to left side, and which this multiplication makes the negative value. But I saw the U rotation data, and it is composed of the vector data. So which means that U rotation multiplied by C theta or U theta should be of the inner product, not the scalar product. Because but the problem is that if you see the original code, the U theta is defined as the scalar, and if you see the library mixing plane enthalpy jump, which is calculate the rotaphysm. Here they made the equation using the scalar product with the magnitude value, which means they cannot calculate the negative value. So that was the problem. So I corrected it using the vector value and the inner product using the %, here. And so you can here before we got the discontinuity result, but after the correction, I made the result with continuous temperature field. So one thing is solved, I think. And this is 5-stage turbine, and here also the temperature field was continuous. So okay, it's okay. And the another problem is that the wall temperature issue. We use the Parry turbine. It is designed by Parry it is originally to make the cooled turbine, but I used only uncooled turbine model, and I just solved, and all the other variables seems right, but except the temperature. Temperature field is very different. So the problem was the the problem was due to the wall temperature. Wall temperature. This is the reference from CFX, but the OpenFOAM made its wall temperature higher than another result. So okay, I will pass. So the problem. So we tested a lot, another version and another solvers too. Here, the OpenFOAM 7 version, raw simple form, is making the good solution compared to the CFX, but the solvers from the form extended having very rare solutions. So 5 minutes left. Okay, thank you. So okay. So I thought that there is some problem in form extend solvers. So I started from the scratch, and this is the energy equation for integral form, and this is the differential equation, and you can drive it, follow this one, and then you can get the ultimate solution. I mean, ultimate equation using the divergence and gradient, and to be used in OpenFOAM with the FOVM, right? So, and then you can drive some equations for many many other variable like internal energy here, or enthalpy, or total enthalpy, or rotaphy here. So, and I try to match the theoretical equation to the equations in the OpenFOAM solver, and I see that another version, I mean the normal version, have the right equations in their solvers here. Here raw pimple or raw simple from Form 7, they match to the theoretical equations. But the problem is that the equations from the form extend having wrong, or some they have some equations that I don't understand well, and they miss some terms like here kinetic energy. So I changed the equation of OpenFOAM, and I can get the right solution. This is the original code, and I changed it. I fixed the I corrected the code, and then I got the right solution compared to the another version. So I wanted to make the MR per solver, compressible MR per solver, to be worked too. So I derived the equations, and I corrected some equations here according to the method before I did, but the answer firstly was not good. So I thought another way that I redefined the about the rotaphy. I mean the rotaphy. I separated the rotaphy into the two terms, just the rotaphy I and the kinetic energy. And the rotaphy definition, origin definition is like this. And here there is same term both sides, so you can eliminate, and then you have this new rotaphy definition here, and you use the rotaphy I here, mimicking the enthalpy form energy equation, and you use the kinetic energy using the relative velocity, and then you can make the solution. I mean, you can get the right solution in my eyes. That So this is the ultimate solution and the result, and I see that the errors was decreased a lot, and in the span graph, and I see that the pressure and temperature, so the values are matching each other. But except there are the turbine temperature is a little bit shifted up in other spans also. It is because I presume that in the mixing plane interface there is some errors in the velocity value, which makes the temperature value a little bit higher. So this is left for the future work. So I think it's time's up. So thank you so much for listening.
Yeah, so we should have for questions. Anyway, we saw 4 presentations, but we have only 2 presentations. But we might use those questions. We can continue with questions afterwards in the slot.
Well, he asked about what's the problem of kinetic energy, right? So the original code there, they didn't care. I mean, they didn't consider the kinetic energy. You cannot see the kinetic energy term in the in equation file. So I just added, but in the original definition of the rotaphy, it already has the kinetic energy into the rotaphy. So so it looks here. Yeah, how to say? The temperature in the flow field looks good, but a little bit different because there is not the how to say that the kinetic energy is wholly not considered. That's why I corrected the kinetic energy into the equations. Yeah.
You did some modifications to the mixing plane.
Some modification?
Did you do some modifications to the mixing plane, or did you?
No, I just changed the this term. I mean this was originally it was the Scholar product. But I just made it into the inner product to calculate the some. It can then it can be calculated for the negative value too. Got it.
Thank you very much. My name is James Parry. I'll be presenting my work on a new conjugate methodology for buoyancy-induced flows. I'd like to thank my colleagues at the University of Bath, Professor Hervé Jacek and Dr. Stefano Oliani for their help, as well as the EPSRC and Siemens Energy for funding this work. So shown on screen now is a section of a typical gas turbine compressor engine. We have on the right-hand side a cross-section of this as shown on the left, and the dark gray parts are the stationary parts of the stator, while the light gray parts are rotating around the central compressor shaft. And at high radius, hot flow in the main gas path heats up, increasing in temperature and pressure as we approach the combustor, while at lower radii, cooling flow is bled off to help reduce the temperature within the turbine. And the interaction between the hot main gas path and the cooling flow creates a radial temperature gradient within the discs via conduction, while in the fluid, the combination of the rotation of the discs and the temperature gradient results in buoyancy-driven flow, which is all via convection. And the interaction of the conduction in the discs and the convection within the fluid is a conjugate problem, with the heat transfer between the two affecting the temperature within each other. And at later stages, the temperature gradients through the disk can result in thermal expansion, which can affect the tip clearance of the blades. And as we approach future aircraft engines, with higher overall pressure ratios, the sensitivity of this tip clearance increases as the size of these cores shrink. And for gas turbine designers, a complete understanding of the temperature and this radial growth is essential when designing new engines. And my work covers a new conjugate methodology to help understand this. And shown on the left is one of these small co-rotating cavities with a heated shroud and that axial through flow passing beneath. And this work will focus on the canonical case of a closed co-rotating cavity, which due to the simplification of the flows lends itself to the validation and modeling. The temperature gradient between that heated shroud and the cooled hub creates that temperature gradient within the fluid. And then close to the radial surface of the disk, laminar Ekman layers form that help conduct heat from the disk to the core and from the core back to the disks in that conjugate manner. And the interaction between the Coriolis forces driven by the shear forces against the disks and the rotation, as well as the temperature gradient, forms a complex fluid motion within the annulus, where hot plumes of gas from the shroud plume towards the hub and cold plumes act towards the shroud. And the interaction of these plumes forms a series of cyclonic and anticyclonic rotating vortices. And these slip relative to the rotation of the disks. And this is a three-dimensional unsteady and unstable problem, with a number of these vortices varying depending on the temperature gradient as well as the rotation of the disks. And this lends itself to computational modeling to help understand this. To validate this, the Bath compressor cavity rig has been used in the closed cavity configuration. A series of 4 co-rotating discs rotate around a stationary central shaft with electric heaters at the outer shroud to model that hot main gas pass, while cooling ambient air is passed through the bore. On the right, we have a diagram of where the probes are located within this rig. A series of radial temperature probes are spread both circumferentially and radially to capture the temperature of the disks, and a pair of unsteady heat flux sensors at the shroud, while 2 unsteady pressure sensors are located 35 degrees apart, and these are used to help capture the heat transfer and the fluid flow structure within the test section of the rig. And at the University of Bath, a collaborative effort is made to help understand the flow within these compressor cavities with both experiments, theoretical modeling, and computation. And my work focuses on the computational aspects, and I'll be hoping to validate my work against the results of both the experiments and the experimentally derived theoretical models. Looking at the methodology, there are different approaches available for conjugate heat transfer. A steady solid coupled with a steady fluid would not be appropriate here, as while it would be very quick, we would not be able to capture those unsteady structures that are iconic to buoyancy-induced flow. However, using an unsteady solid with an unsteady fluid, while capturing these structures, it would require an excessively long convergence time. And this is due to that difference in thermal inertia between the fluid and the solid. We've used an unsteady fluid coupled with a steady solid, as we can capture these unsteady structures while achieving a convergence in a more feasible time. So we've used a 3D coupled sector with a 360-degree sector size, and this was done to ensure that the development of the structures is not impeded by any periodic boundaries. An axisymmetric multi-block mesh has been used, which has been conformal at the fluid to solid interface with 4.6 million cells over the 4 domains and 27,000 CPU hours used for convergence. OpenFOAM version 2006 was used with the unsteady Reynolds average Navier-Stokes equation in the compressible form with the K omega SST transport model. However, some new implementations were needed to help solve this, and I'll just go through those now quickly. The first one was the conjugate solver. The available one in OpenFOAM 2006 is CHT multi-region foam, and this solves the equations in the absolute frame of reference. We have implemented a new solver which solves these in the rotating reference of frame. And this was essential to help capture the development of the boundary layer on the radial surfaces of the disks in a feasible number of elements. And this was found due to round off errors within the code when solving in the absolute frame of reference. key implementations are using the available SRF module, which was existing within the code, but in a incompressible state. And this has been included into the new conjugate solver, in particular with the SRF foam section, which has the Coriolis and centrifugal forces needed in the momentum equation. And also added was the term added to the energy equation used to help capturing the work done by the centrifugal body force. And just shown on screen now is part of the momentum equation of the code. Note the SRF.SU being the source term for this rotational package, which covers the Coriolis and centrifugal forces, as well as a change to the kinetic energy KREL for solving everything using the rotational reference frame. The other implementation was a new conjugate boundary condition. The existing conjugate boundary condition is a sliding plane, which passes the information of temperature directly between coupled cells. On the right here is an example of a non-dimensional temperature profile taken at a single radius within the fluid. With the sliding plane in space, this is passed directly into the solid. However, I'll show you in a second why this is actually an unrealistic result. And I've implemented a new version of this code, which has a mixing plane, which passes a radial average of temperature from the fluid to the solid. Shown on screen now is the existing methodology for this current boundary condition. And this is from the position of passing the information from the fluid to the solid, where a series of simultaneous equations resolving equaling the temperature at the interface, as well as making sure that the heat flux is equal and opposite when passed between the two. And this uses a mixing fraction notated as omega. My new version of the code adds an extra step, which calculates the average temperature when passing this across from the fluid to the solid. For the initial first time step, the information for the neighboring patches is captured onto a master processor list, and all of the cells are grouped into radial groups. Now, the mesh being conformal and bounded within radial groups allows us to, and because it's not changing between the groups, allows us to have a consistent ordering. So as this is not changing with time steps, this is completed once. All of the radial groups are identified, and a new class was created within the create field section to help store this information. And this is then saved and distributed to all the processes. And in subsequent time steps, the temperatures for each radial for the whole patch is collected on the master processor. The groupings are made and an average temperature is found for this radial band. And this is then passed back to each processor and allocated for the corresponding cell. And just to show how this actually affects the results, I have a instantaneous slice of the midspan of the fluid there on the left, and the boundary condition of the solid as seen from the solid that has been received from the fluid. And if you notice on the left, you can see two clear cold plumes that are from these unsteady structures, as I mentioned before. And we can see that in the solid boundary, these are then passed instantaneously. And this is because we're using a steady state. But every single time step, the solution is then perturbed as these radial structures slip relative to the rotation of the disks, which means a convergence can never be reached as we constantly perturb the solution. By implementing a mixing plane, we can actually get the axisymmetric solution within the solid. And this is akin to the time average solution of the converged solid. And as a result, within the mixing plane, we can see that in the fluid core, we have these rotating rate structures that we see in buoyancy-induced flow. Shown on screen are the model boundary conditions for from the experimental rig. The only implemented temperature conditions are a heat flux at the shroud, which is arising from those radial heaters, and a cooling flow at the bore. To characterize the different cases run experimentally, the rotational Reynolds number was used, which characterizes the rotation of the disks, as well as the buoyancy parameter, which indicates the amount of convection occurring within the fluid. And this can be characterized by the difference between the shroud and the hub in terms of temperature. 4 cases were selected that cover a full range of these rotation speeds and temperature gradients. And the other boundary conditions are shown here, and further information is available within the literature that's recently being published. We'll start now by looking at the full temperatures for the model in terms of non-dimensional temperature. As shown here, this is for case 2, which is a high temperature gradient, low rotation case. And the non-dimensional temperature has been characterized by the shroud temperature, which is a time and circumferentially average temperature for both the shroud and the hub. If we move on now to the experimental disk wall temperatures, starting from here, we have the non-dimensional radius on the y-axis and non-dimensional temperature on the x-axis. The results for case 2 have been modeled, and if we plot that, we can see that we're able to capture that trend of disk temperature. And note that for most of the cases within this field, use fluid-only simulations, where this is actually applied as a boundary condition. And in our case, these are predictions of temperature being a conjugate model. We can also compare this to a theoretical core temperature derived within the uni. And once again, we're able to capture that trend. If we also then look at a high rotation case, we can see that this has actually once again captured the results well, but we've also managed to capture that change in core temperature gradient. And that addition of the centrifugal body force within the energy equation was essential for capturing that change in temperature gradient. If we move to the fluid structure results, here is an instantaneous snapshot of that normalized pressure. With the disk rotating in a counterclockwise, we have a series of those cyclonic and anticyclonic vortices. And for this case too, experimentally recorded, there were 3 pairs of these rotating and counter-rotating structures. Note the arrows in between these structures mark the location of these radial plumes. And if we plot the normalized radial velocity, we can see that. And with the animation of the disk rotating in a counterclockwise direction, we can see these radial plumes slip as these structures slip relative to the disk. And experimentally recorded, these were about 99% speed for the structures relative to the disk speed. And this is once again captured within the simulations. We can also then look at a higher rotation case, and we can see that the number of these structures change, moving from 3 to 4, which is once again captured experimentally. Lastly, one other thing we looked at was a change to the compressibility parameter. And this is a parameter that characterizes the rate of kinetic energy to the heat transfer in the system, with a higher value of this value chi relating to more conduction within the system. And a 5th case was run at a very high value of this, which indicates that there is conduction in both the solid and the fluid. And if we start by plotting the results from cases 2 and 4, we can see a similar trend with these in terms of disk temperature results. And with conduction occurring in both the disk and the solid, we can see a deviation for this case. And if we plot the theoretical solution for a circular cylinder, we can see that this case 5 is approaching this theoretical conduction solution. And looking at the fluid, we can actually see this, where we no longer have those strong buoyant structures associated with buoyancy-induced flow, instead having very weak convective forces still slightly present, indicating that conduction is not completely dominating in the fluid. So to conclude, EURAN seems to be suitable for conjugate simulations of closed co-rotating cavities. There's a lot in the literature about LES being essential, but for this closed case, EURAN seems to have captured all of the fluid characteristics that we expect to see. And that the conjugate approach is able to independently validate a lot of the assumptions made by the theoretical models within the group. And lastly, that for solving buoyant flows in co-rotating cavities, that the Navier-Stokes equations should be solved in the relative frame of reference in order to capture the heat transfer from boundaries with an affordable number of elements within the mesh. And that lastly, a mixing plane should be used for this coupling to overcome the difference in thermal inertia. Thank you very much for listening. Are there any questions?
Very much.
The need, so the question was not fully understanding the need for the mixing plane. As this was the conjugate simulation, the only available boundary in OpenFOAM version 2006 was that sliding plane. But because we're trying to run with a steady solid with an unsteady fluid, if you have that direct coupling, as the steady solution instantly converges to whatever's being passed from the fluid, it meant that you constantly perturb the solution. So as a result, a convergence was never reached, because the difference in that solid domain is then passed back into the fluid. So you constantly disrupt the formation of the vortices. In the experiment, when you've run for a long transient, effectively the disk turns into an axisymmetric distribution. So we needed an axisymmetric solution within the solid, which was achieved by passing that radial average from the fluid to the solid. for my sponsor company, further interest is needed for that 3D coupling. Hence, 2D 3D coupling could have been viable in this case, but there was a drive for a 3D coupling, hence the need to implement this boundary condition.
Could ask about, you mentioned Ekman layers. Did you have to do some special treatments to capture those, or how did you solve the boundary layers?
That was part of that. Oh,
I don't know.
sorry. Do you want me to repeat that?
Yeah,
question?
I don't know.
So the question was about the development of the laminar Ekman layers and whether any treatment was needed. And that was actually the important part of using that relative frame of reference solver. So when we solved in the absolute frame of reference, we noticed that their formation was disrupted. And in particular, the heat transfer was not very well captured. And as a result, the core temperature distributions were heavily affected. But as soon as we moved to that relative frame of reference, we overcame those round-off errors, they developed properly, and as a result, we could actually capture those correct plumes seen from the shroud towards the hub. So no particular need, but that relative frame of reference was needed. The only other way of overcoming that would have been an excessively fine mesh to prevent those round-off errors. And thanks to Professor Herb-Yasak for helping solve that problem.
Still have to use the Y+ values again.
Yes, yeah, we still have all of the mesh has Y+ of 1 for all of the interfaces. Yes, yeah.
Okay, so let's just go to this concept.
The time step. So we yes, it's transient simulation. So we used the variable to initialize it. We used the adaptable current number and kept it less than 1, but it was approximately 5 × 10⁻⁵ seconds for each time step. For the animation, you saw that. Yes, 10⁻⁵. Yes. Yeah, it was a very fine. It's quite unsteady when it was first initialized, but that is related to the cells. So if there is a difference in the thickness of the cells, so this is how the conjugate boundary is currently implemented in OpenFOAM. The delta F corresponds to the differences in the cells between the solid and the fluid. So the delta S may, for the solid, you don't need as fine a mesh. There's no point in putting a boundary layer, but that means that the interpolation is needed for getting the temperature up the interface. So it solves that mixing fraction.